Nice to meet you. It doesn't work. You can find it doesn't work.
Oh, yeah.
Yeah.
Sorry about this. You have to put it here.
Okay. Okay.
Hi, everyone. Let me introduce you Zheng Zhao, postdoc at the Uppsala University, who previously obtained a PhD at the Aalto University, here to talk to us about convergent stochastic filtering with moment representation and quadrature.
Thank you. Hope you're not hungry because I'm pretty hungry already, so I might lower down my voice a bit. So if you cannot hear me clearly, please feel free to interrupt me. I will come to you and explain to you. So in the last 2 days, we have seen a lot of beautiful results on stochastic processes, calculus, and static optimizations. So today, I would like to steer our discussion topic to something different, which is stochastic filtering. So it's a joint work with the mathematician in Finland, Juha Samavori. So let's just briefly recall what is filtering. Maybe you know, maybe you don't know. So here is our model definition. Assume that we have some Malkovian kernel. We have a random variable xk, given xk matters 1, follows some conditional distributions. And this Malkovian kernel can be given by any discrete time statistic models or stochastic differential equations. And then we have a likelihood model, some people call it initial model, with some measurement random variable yk. The condition on the state follows some likelihood distributions. So the so-called filtering is to compute the distributions of the random variable xk conditions on all the historical measurement random variables. So different distributions. And we all know that the computation is quite difficult to do in the sense that it is hard to compute the exact solution. So in engineering, we have a lot of useful approximations, for example, like Gaussians. So it's the idea is that we can form some approximate distributions like p hats, so that the p hat is Gaussian with some mean and with some covariance metrics. And this is known as extended common filter or a Gaussian sigma bond filter. And the benefits, the merits of these Gaussian filters is that it really works very well for a lot of engineering problems. So if you have some problem and you want to know the solution very quickly and dirty, then you just apply this Gaussian filters and you get a solution very fast. But the downside is that there's no convergence guarantee. So you have to model and you know that your solution is apparently not Gaussian, then I have no idea about the convergence. So alternatively, yeah.
Yeah, in the linear case, you have convergence.
Yes, yeah, linear case.
So what's full convergence here for? You mean you
convergent in terms of distributions?
So you mean close to Gaussians or
no, the distributions, because we have approximate distribution, right?
So the real one is not Gaussian. So you
Yeah,
like to,
if I have a model that I explicitly know that the true solution is not Gaussian, so then I cannot hope for one the convergent solution for that.
yeah, so then it's okay.
Yeah.
It will never converge in the sense that there will be no.
And I think there will help for the maximum a posteriori estimate to converge to the true frequency of the data.
Okay.
That is possible, yes.
Yeah.
Okay, so an alternative approach is by using another representation of the approximation, is by using multi-color samples. So essentially, we have some discrete measure with weighted samples, weights and samples. This is known as sequential multi-color techniques, and we have particle filters. And the pro is that on very mild conditions, we can establish convergence results. In the sense, we have some metric for convergence of the approximate to the true distributions. But the problem is that in practice, we really need some good proposal distributions in order to have very efficient sampling scale. Because sequential multi-color use sequential importance sampling. So we really need to have a good importance distribution. And another problem is that inevitably we might need to use resampling scale in order for the weights to be not degenerate. And this might introduce some additional variance in your estimate. So today, I would like to ask a different, we would like to resort to a different representation of the future distribution approximation. Is that we would like to use a sequence of moments. So instead of computing the full distribution, we would like to solve a projection of the distribution up to the moments. So here I use notation M, Kn means the moments, this is the nth moments at the kth time step. There is a definition, the moments of the future distribution. Now suppose we have a collection of them at time k, let's call it big letter big N. Suppose we have a collection of it. So can we use such sequence to approximately represent the future distribution? So if we want to do that, the first question is, so how do we actually compute the moment? And because we are using filter, so one key feature of filter is that it is a recursive algorithm, in the sense that we start from some known estimates, and then we use these estimates to estimate the distribution in the next time step. So it's a recursive algorithm. So if we want to compute the moments, so how do we form a recursive computation, a recursive algorithm? And then the second question is, okay, so suppose there is some kind of algorithm to do that. Can we get some convergence guarantee? Like, will the moment generate some kind of convergence measure so that the convergence converges to the true distribution as we increase the order of moments to infinity? Okay, so the computation of moments is very easy. So we just need to recall the basic equations of the filter. So for any discrete time filter, we can always decompose the filter into two steps: prediction and updates. So for prediction steps, suppose we know the distribution in the previous time step. So this is the previous future distribution. Then you just need to make a prediction through your Markovian kernel, which is a dynamic state space model. Make the prediction to compute the so-called predictive measure, and then you do a Bayes, simply do a Bayes updates. So the radon Nicoleon derivative of the filtering distribution with respect to this prediction measure is given by the probability functions of your emission model. And then, so this we have recursive computation. So we just need to draw some non-initial condition to recursively do the future. Okay, so to use moments, we just need to replace this function f by some monomials. We can of course use all kinds of polynomials, for example, modified polynomials, central moment, scaled moment. But here for simplicity, let's just use monomials so we get raw moments. Then just choose the function f to be any monomials. Then here is the algorithm. And for this function, expectation of xk power n, right? And this conditional expectation, you can write down this analytically for most models. So once you have a steady state model for some Gaussian or maybe some arbitrary distribution, I believe it is easy to analytically write down this conditional expectation. For example, for Gaussian, you can do it by Easterly's theorem or so-called weak theorem. And then, so since this is a function which we know, function of x. Now suppose that if we know the moments of this previous future distributions, so we're asking, can we use those moment information so that we can compute this individual? Now suppose that we can, then suppose that there is such an algorithm let us to do so. Then with these moments, then we can compute the arbitrary moments of this probability measure. And similarly, for the update step, then since we know the moments of this, so since we can compute the moment of this measure, then we can compute this quantity because this is a function which we know by model construction. We can compute this number, which is non-linear constant, and then we can then compute, of course, the moments of this next filtering probability measure, just by evaluating this function with another multiply with another monomial. Then, okay, so then it is clear now that to run such a filter, we need following k enablements or k functions. So essentially, it's that suppose we have some distribution P. If we know some moments of this property measure, we don't know the complete information of the measure, but only this moment for Mn, a fraction of the moment. So we're asking questions. So can we find some quadrature rule with quadrature weight and quadrature lambda, so that we can approximate this integral by this finite sum? And I also ask that this quadrature rule must be in some sense optimal. Okay, so if we want the quadrature node to be optimal in the sense that the integral will be exact for polynomial integrants, then we will need to use so-called the orthogonal polynomial approach. So to do this approach, we need to introduce some technical prerequisites. So let's define inner products between the function f and g as an integral of fg under this probability measure. And then it will be clear that moments at hand to up to order 2n minus 1 collection of moments, they actually generate a system of orthogonal polynomials, which satisfy a three-term recurrence relation, which is very widely known. And it has this recurrence relation has coefficients alpha and beta. So C0 to Cn, they are orthogonal polynomials in the sense that the inner product between them are either 0 or 1. So alpha and beta, alpha equals to the inner product between the orthogonal basis at a minus 1 with so essentially a projection of the operator z onto the basis a minus 1. And this operator z is a multiplication operator. It's defined in a way that the z if you apply on function g is equal to this argument multiplied with function, so multiplication operator. Then so the yes.
So far everything was one-dimensional.
Yes, I will talk about small dimensional.
Okay, because this is where my dimension is different. Right?
Sorry.
This is the part where my difference were in different. But
This is univariate.
exactly right.
Yeah. I'm going to talk about multi-dimensional data.
Okay.
Yeah. So the essential idea of this orthogonal polynomial approach is that we can actually use the roots of the highest order polynomial Cn as our order nodes. Then you might ask, okay, so what is the motivation behind it? Why do you want to use the roots as a order nodes? Suppose there's a good reason behind it, then how do we actually compute the roots and how do we compute the associated weights? It turned out that it is, okay, so to answer the first question, so the motivation. So informally speaking, the roots of the orthogonal polynomial have very nice property. So essentially they can nicely cover the support of your property measure. Here is an example. It's not showing the animation on iPad.
Oh, okay, you could open an echo, but we
Yeah. It's yeah, it's not working.
You just hang on a second.
Okay.
Sorry about that.
Okay.
Oh yeah, sorry. I think.
Okay, then we
have
can
it.
go without animation.
Right.
I close that.
Okay, no worries. Yeah. Sorry about that.
Yeah.
You can, by the way, also point here. Like that.
Yeah. Okay, so anyway, if you try to increase the order of polynomial, you can see the root spread very nicely the support of the distribution. Then another motivation, which I also think the most important reason, is that we can calculate the weights in a clever way such that the integral be exact for certain order of polynomial integrants. So if you recall Weierstrass theorem, Weierstrass theorem, then you can easily establish the convergence result for any continuous integrand on like a compact domain. So for 1D case, the convergence rate can be in a factorial space in terms of the order, and compared to Monte Carlo approach, which is very fast convergence. Compared to Monte Carlo approach, we can also give exact equations for some specific equation compared to Monte Carlo approach. And then next question is, okay, so how do we actually compute the root? It turned out that it's quite easy, just need some basic linear algebra. So cheers. But here, the small fonts, which I don't want to show you, but I have to show you is that it's for low dimension only. So how do we do that? A very classical result from like Golden and Welsh, so that the roots that we want to compute, they're essentially given by the eigendecomposition of a so-called Jacobi matrix. The Jacobi matrix is the aggregation of the three-term recurrent distribution polynomials, alpha and beta, if you recall in the previous slides. And this, by definition, is essentially a matrix representation of the operator data. Right? It's a matrix. I can see every element is projection of the operator onto the spaces. So to compute the Jn, then we just need to compute such a matrix, and then we just apply some Gram-Schmidt, also normalization, so that to compute this matrix. Yeah. Then to do so, we need to define a sequence of linearly independent spaces. That's called P0 to P(n-1), whereas phi just simple mononomial functions. Then we will have a Gram matrix, Gn, matrix of those inner products. So by definition of the inner product, this will be a matrix of moments, essentially. And then by definition, this will be a Gram matrix. Then we just do a Zheng decomposition of the Gram matrix, and we can also normalize any matrix representation of the operators. So the Hn will be the metric representation of the operator into the linear basis. Then we just apply Gram-Schmidt here to here, and we just can compute the Jacobi matrix Kn. We essentially just do a Zheng decomposition and then solve two linear system. We can compute the Jacobi matrix. So here's the algorithm. Suppose you have a bunch of moments, you just aggregate all the moments into two matrices, and you do a decomposition of Gn, and then solve two linear system, and you compute the eigen decomposition of the resulting matrix. So down to bottom. And the complexity of this algorithm is around cubic in the order because of the Zheng decomposition. But then the question is also, okay, sorry. Here's the example in 1D. We have some distribution, some Gaussian mixture, and some uniform, some gamma distribution, and this is the result, the visualization of the quadrature nodes and the quadrature weight, the height represents the weight of the quadrature. N equals to 11 means we are using 22 moments. So this result, you can see it can well represents the distribution. Then the next question is, okay, so how do we do the multi-dimensional case? It turned out to be, in my opinion, from my perspective, it's not easy. There should be animation like someone sweating. It's not easy, in my opinion, because Tuesday I was talking with Terry Leong. I mean, with him, it seems like he has some kind of a recombination of various techniques to tackle this problem, but I'm not familiar with. I say the problem is difficult because we have to deal with all of the tensor algebra and all the theories, which is really not my thing. So anyway, so in our approach, we can came out with a generalization of the 1D case at the cost of very extensive computation. So the computation complexity will be a cubic in number S, and S is a binomial of the order and the dimension. So this is very disaster if you have very huge dimension. Yes, please.
Isn't it true that kind of NCMC standing to integrate is independent of the dimension? Think people may?
No,
No.
I
I always heard people say, you know, you just sample and then you integrate from the distribution. It
is in some sense, right? So the convergent in N, but yeah, there's always square root N, the functional of the choose base and others. Right. You can get exponential base if the functions. Okay, but so now exposing the N testing, but almost concepts.
And here we're talking about constant.
Uh,
But here, like, so S to the 3 is dependent on 2. Which sense does the dependency D come in here? Like the
D is a
error.
sorry?
The numerical error. Like
No, this is a computational complexity, not the error.
Right, okay.
Computational complexity,
Right.
not the error. Mhm. Okay, so I'll just basically sketch the basic idea. So for multi-dimensional, we need to define some multi-dimensional monomials with respect to some multi-index, like so bold-based N. And then we will also need multi-dimensional orthogonal polynomial of Cn. You can assign any partial order of the Cn as long as we define the first orthogonal polynomial must be a constant one. And then we just need to construct a multiplication operator for each dimension. So let's call it delta I for each dimension. And then what we need to do is just we to compute the metric representation each I for each of the multiplication operators. Then just very basic the theory now is that if we have some continuous function or some compact domain, then the operator extension of the function, like say a function some with RD to R, then you can define metrics. You can define a function which takes the operator as input, which output the operator by using spectral integrals. You can show that this turns out to be also a multiplication operator in a way that this operator, if you apply to any function G, is equals to F multiplied with Gx. So with this in mind, then we can approximate the integral, right? By thinking that okay, it's trivially a projection of the F onto the first basis, because this is constant 1. Then is essentially a first element. It's a projection of this operator onto the first basis. And so if we can have in some sense matrix representation of such operator, then this essentially can be approximated by the first element of such matrix. And with some algebras, we can show that such matrix is can be given by this sum, where the lambda ni and this ui, they are the eigenvalues and eigenvectors of each operator that are the metric representation onto the linear basis functions of each operator. I will ignore all the details. Sorry. So here is the basic results, relation of the results. We have 2 examples. Gaussian sum has a uniform of some polygon area. And those scalar points represent the quadrature rules. And the size of the scalar point represents how large is the weight. You can say that it can well represent distribution, but the one key problem is that it can give negative weights. So we have sign vector. And so two important results is that this quadrature method is exact for any multi-dimensional polynomial of degree 2a-1. A second result is that if you try to apply this method to the filtering problem, then in each step you do the moment integration, and this will generate so this moment filter, it will generate discrete distribution, which you use the quadrature weight and quadrature nodes as the approximation to the distribution, and it will converge weakly to the true filtering distribution. Convergence weakly and also convergence in moments as you increase the order for every time steps. And here's the results. So we want to test the convergence. So we have a linear Gaussian model for the filtering. So we can compute the exact solution by applying comma filter. Then we just compare the result against the comma filter, and we can test the convergence. You can see that as we increase the order, so here 6 moments, 14 moments, 22 moments, and 30 moments, we can establish asymptotic convergence. And here is the index for the time. And to make it more clearly, here's the error of the mean estimates and error of the variance estimates. You can see that as we increase the order, the errors decrease in a very fast speed. So this is plotted in log scale, and it almost looks like a line. So it's not exponential speed fast. So I cannot believe that. So it might be some very high order polynomial speed. And particularly to compare to particle filter, right? So when we're using around moments, around 10 moments, so when n equals to 5, we have around 10 moments. So it's already far better than that of particle filters with 100 samples, 100,000 samples. Yeah.
Am I right in assuming also that in wall clock time, the moment filter would be much faster?
I will show you the result about conversion time. Then we will also test the results for some nonlinear models, because we're applying for common feature, of course, is for linear. So we have nonlinear SDE. The initial condition of the nonlinear SDE is some Gaussian mixture. We will try to create some non-Gaussian solution. And the Merriam model is a Bernoulli with some nonlinear bijection. As a side note, that if you try to apply extended common feature for this model, it will fail by definition. You will get all zero. Okay, so here's the result. We can say that, okay, for this nonlinear model, it also converges and also converges very fast. In particular, if you try to compare with particle filters, the convergence result is very good compared to Gaussian filters. And then about the time cost. So if we try to use this like 30 moment, do we really have a problem with time? Actually, no. So for low dimension, this method is very efficient. So if you have used a giga a lot amount of moments, so 30 moments, in the time, which is around 0. I don't think value, is still far better than the particle filter. Which one? The particle filter. It is still faster than particle filter. So with the same accuracy, it's faster than particle filter, essentially. And here's a visualization of the results. The black solid line represents the true density functions, and the purple line, which you cannot see because it's completely overlapping with the true solutions, represents the estimated probability function by the normal filter. And the gray area represents the histogram of the particle filter. You can see that's the basic for the size. But to clearly see the difference, particularly compared to the particle filter, we actually need to zoom in and try to plot the characteristic function, which is shown on the right-hand side. So this shows the value of the characteristic function. You can see that this black line is the true value of the characteristic function, which completely overlaps with the moment filter. And this dashed very gray transparent line is the estimated result by the particle filter. You can see a large deviance and large errors compared to the true solution if you try to use the particle filters. Well, the Gaussian filters, which is this circle, is completely open.
So
yes,
you will have
5 minutes.
Wouldn't the theory of particle filters predict that it should be accurate? Or like what was wrong?
I mean, if you try to increase the number of samples to infinity, of course, it will.
Just need so many.
You just need more samples.
10,000.
This is 10,000, yes. Okay, then another application of future is that we can do parameter estimation. So we have to know that we have some unknown parameter theta 1 and theta 2. We want to compute some likelihoods so that we can optimize the parameter by the variables. Then we can also apply the moment filter to do this application too. This line represents the true parameter value, and these are the results by Gaussian filters, extended Gaussian filters, moment filter, particle filters. I think particle filter is actually completely off for a reason, because we cannot really use gradient-based optimizing for this application. So we have used another particle filter, which is called particle filter with continuous resampling, which is use optimal transport to replace the resampling steps. In this way, it will give you the correct gradient. So you can see that the results with the particle filter is quite close for this parameter and for the another parameter. Okay, and this is for result for 2D experiment with some pre-predator model. Here's the results compared to the absolute error. Particle filter with moment filter with n equals 5 and n equals to 7. So 10 moments, 14 moments. You can see the error in time. It is still bit better than particle filters. So you might ask, well, why can't I increase the n to 15 like I did for 1D? Because of the competition. So in conclusion, we have shown you how to compute integrals if we know the moment information of the probability measure. And we have also seen how to apply this method to solve the fusion problem. So in my opinion, this is not a groundbreaking result, but it opens up a lot of interesting problems, in particular the computation. So like I asked, what's the problem with higher dimension? So with this current approach, you can see we have dimension 5, and we want to use 20 moments, then we will end up with this number of operator nodes. How many digits? 1, 2, 3, 4, 5, 6. I don't know, I cannot number it. So this computation is a problem for high dimension. And also another problem is that the future is a propagation of moments, approximate. So this approximate moment, they do not guarantee that we will have positive definite grammatics. So it might have stability problem, depends on your applications. So maybe similar to sequential Monte Carlo, we might also need some resampling scheme so that if it's approximate moments, then we can find a completion of the moment sequence to make it positive definite. So anyway, the code and the preprint, they are public available. So if you're interested, let's get it. Thank you.
Any question? Yes.
When you showed the quadrature rule that you had, which is that you have negative weights, right?
Yes.
But then, well, it's pretty wondrous. Does it use support response? Points that are in your quadrature measure, they are also the support of the region, right?
So the quadrature is definitely a product. So right, we would be a rectangle.
Right,
But because now it's weight in force of
yeah. So just the people back to Chocolate, so like 7 years ago, but the right produce algorithms where they are getting positive and essentially also